Okay, I'm taking a previous example just a little bit further now. Okay, so go back and check one of the examples on compressibility where we took refrigerant 134A at 16 bar and 100 degrees Celsius, and we found it two different ways. Now we're going to add the ideal gas model onto it. So the best way to do is just use the table. You can look that up and get that value shown there. Okay, then you can use the compressibility chart like I showed in the previous example, and we found this, which is pretty close to that. It's a little off, but pretty close. Certainly the table is better to use than this. Not only is it more accurate, but it's faster. Okay. Now, the last way we're going to do it is using the ideal gas model. And the ideal gas model is PV equals RT, right? Where I know my pressure, I know my temperature, I just need R. Okay. Now, R, remember, is our bar, which is universally constant, divided by the molecular weight for the object or the substance that we're using, which in this case is 134A. Okay? So again, our bar is what's given here at 8314. Okay? Now, I've got refrigerant 134A, so I have to go look up its molecular weight here in table A1, and I can see that the molecular weight is 102.03. So I take that 8314, which is universal, divided by the molecular weight, which is 102.03, like so. Okay. So from that, okay, I plug it in up here to find my volume, right? So my volume is going to be that R, which I just calculated, 8314 over 102.03, okay, times the temperature, which is again is 100 degrees Celsius, okay, but I need to convert that to Kelvin, so I add the 273, and I'm going to divide that by my pressure, which is 16 bars, so 16 times 10 to the fifth. So everything's in its base units. I can plug this in, and I find the volume of 0.019 cubic meters per kilogram. Now you'll notice this is actually quite a bit off from this one, okay, and even more so off from that one. Why is that? Okay, you'll remember, and again you can go back and look at that previous example. Okay, in this example, Z equaled 0.86, that compressibility factor. For here, the whole idea behind the ideal gas model is Z equals 1. Okay? Well, Z clearly doesn't equal 1. That's why I get a value that's off here. Okay? So for the ideal gas model to be true, Z has to approximately equal 1, which you'll see as I converge to a Z equals 1, right? That's when I've got a very high temperature relative to the critical temperature, or a very low pressure, because I got this flat line going across the top for high temperature, and at low pressure it goes. Okay, so I'm at a pretty high pressure here, okay, and a relatively low temperature. So that combination makes it not an ideal gas. Okay, now moving forward, it'll become obvious what's ideal and what isn't. Okay, but that at least shows you, when the ideal gas model is applicable versus when you should use the compressibility chart.